Okay, one more day of related rates. This time we are going to be dealing with trigonometry because I know how much you guys love trigonometry. How do I measure a spinning object? I actually don't know why the title of this is called a spinning object. I mean, I guess the Space Needle is spinning, but it's not really related to what we're going to be working with. It says here, Seattle Space Needle officially reopened on the first day of Seattle's World Fair in April 21st, 1962. It features a flying saucer revolving restaurant that's 500 feet above the ground. The restaurant is accessible by stairs, 832 steps, but most people take the elevator. Suppose you are across the street having coffee, watching the elevator ascend and descend. Your window is 100 feet above the ground and is 2,000 feet away from the Space Needle. So here's the situation. You are here, and you are 2,000 feet away, and you're looking up at the elevator. The elevator ascends and descends at a constant speed of 14 feet per second. Let theta be the angle of elevation to your line of sight to the elevator. So this is theta, that's going to be your angle of elevation, and h is going to be, h of t is the height of the elevator above the ground. We're going to make a prediction, describe how the rate in which our angle changes over time. Explain what your answer means physically as you watch the elevator rise. So how is this rate going to change? Is it going to be faster or slower, or is it going to be constant? We're going to find that out. We're going to write an equation for d theta dt. So the first thing we need to do is we need to talk about what is our equation that represents our situation. So our situation is a right triangle where we have theta, we are 2,000 feet away, and we have d theta, or dh dt. This is changing, our Space Needle, our distance is changing, and we have our rate is changing. So our rate in which our theta is changing. And our equation then that we are going to start with is how do I relate my opposite side to my adjacent side in with our theta? Well, that's just going to be tangent. Tangent of theta is equal to our opposite, which is h, and our adjacent, which is 2,000. So that's our equation. We need to turn this into rates. So of course we are going to take the derivative of everything. So d dt of tangent theta and of h over 2,000. Our derivative, before we actually take the derivative here, we need to solve, oh, actually it doesn't matter, but I don't want 2,000 out in the denominator. I'm going to multiply it to both sides. So I have 2,000 d dt of tangent theta and dh dt. We'll just write that part. So what is the derivative of tangent theta? The derivative of tangent is secant. So 2,000 secant squared, it's secant squared theta. And then the derivative of theta is d theta dt. And that equals our dh dt. Oops. We want to solve for theta, so we're going to divide both sides by the 2,000 secant squared. So we have d theta dt equals dh dt divided by 2,000 secant squared. We have secant squared in the denominator, and when we have 1 over secant, that's the same thing as cosine. So if we had secant squared, that's going to be cosine squared. So we can rewrite this as cosine squared theta dh dt over 2,000. So that is going to be our equation that represents our change in our radians over time, depending on our height. So we want to interpret this in context. We also have some information here. So what does this represent physically? It represents our speed in which our angle of elevation when we're looking up at our elevator, how fast our radians are changing over time. And we have to determine, like, are we going to be having the fastest time when we're looking at the top? Like, is it going to be growing the fastest? Is this going to be growing the fastest here? Or is it going to be growing the fastest when it's flat? It's not going to be somewhere in here. It's either we are speeding up as this elevator is increasing, or we're slowing down. And we're going to need to go ahead and decide what is going on. We have some information, so let's go ahead and fill out our know, want to know, and snapshot. So we have our know, we have our want, and we have our snapshot. We know that it's moving at a speed of 14 feet per second. So dh dt is 14 feet per second. We want to know what the radians are, and that depends on whatever our snapshot is. So our snapshot is either going to be 0, so h is going to be 0, or h is going to be our maximum height, which is 500. Yeah, 500. It's not going to be somewhere in the middle. So our situation is going to have two triangles. Either we have a maximum height of 500 and 2000, and this is going to be our theta right there, or we have a triangle that doesn't have any height, so we're going to call this 0, even though I want to represent it as a triangle that has some height, but it doesn't have any height. It's 0. So it's either going to be flat with our eyesight. So go ahead and make a prediction now. What do you think is going to be faster? Is our radians going to be growing faster when it's just started? Or is our radians going to be growing faster when it reaches the top of the restaurant? So how are we going to figure this out? Because we're going to plug things into this equation. The only thing we need to plug in here is our dh dt, which is 14 feet. And then we need to figure out what our radians are. So we need to solve for our radians in our two situations. So in order to figure out our radians for this situation, we could say the tangent, so tangent of theta is equal to opposite, so 500 over 2000. So we'll say that theta is equal to the inverse tangent of 500 over 2000, which is going to be 0.2449, or theta is equal to the inverse tangent of 0 over 2000, which is 0. So those are going to be my two radians that I'm going to compare. Let's go ahead and plug in our 14 feet per second so we can simplify our problem. So we have d theta dt equals cosine theta 14 over 2000. This is going to simplify to, we divide both these numbers by 2, so we'll have 7 cosine squared theta over 1000 equals d theta dt. This is our rate in which our theta is changing in respect to whatever theta we're talking about. In this case, we are going to have two values, this one or this one, and we're going to compare those two. So let's do 7 cosine squared of 0.2449 divided by 1000 versus 7 cosine squared of 0 over 1000. So if you type these both into our calculator, we're going to get either 0.0065 radians per second or 0.007 radians per second. So which of these two are larger? This one is increasing more. And if you think about it, when we are looking straight across, the change, so when we're looking straight across, the change in I guess the difference between these two. The change in some height is going to have a more impact on your angle of elevation than when we're looking across at a height of 500. This change is going to have less of an impact on our radians than this change will. So it makes sense that when we're at a 0 height, it's going to be a more of an increase in radians. And then the last thing we're going to answer here is, oh, that is our last one. Our theta is changing the fastest when the elevator is level with your window, with you, or your window, or wherever you are at. That is, what is it, 100 feet above the ground? Yeah. You are 100 feet above the ground right here. So when it is level, that's when the elevator is increasing your angle of radians, your angle of elevation, the fastest. Okay, so that was kind of a long one. I hope that was all right. Please tune in if you have any questions later on Friday. Your assignment is just going to be 3 problems. And I look forward to seeing you later today.